Hello friends, welcome. This is second lecture for course A Hands-on Robotics, and today we are planning to discuss about direct kinematics and inverse kinematics of this particular manipulator. So this is simplest kind of manipulator consisting two links and two joints. So as you can see here, so this is from this joint 1 to joint 2, this is link 1, and from joint 2 to this end effector, this is link 2. So to drive this manipulator, two stepper motor has been used, one at joint 1, this is joint 1, and second is at joint 2. So, and this is end effector. Okay, and at the end effector I placed a pen that can be lift up and down just by using one servo motor. So in this class we will derive first direct kinematics and also inverse kinematics. So these are geometric parameter like from joint 1 to joint 2, length is L1, and from joint 2 to end effector, this is L2. In the sense, length of link 1 is L1 and length of link 2 is L2, and joint 1 is revolute joint, as you can see. Also joint 2 is revolute joint. So we will use trigonometric relations to derive direct and inverse kinematics. This is simple and easy to understand. Later, rotation matrix can be also used, but for simplicity, I am avoiding that. So, 12th standard student can also learn what is application of trigonometry in robotics and in daily life. Generally, they ask what is application of trigonometry. So, that's why I am using trigonometric relations to derive inverse and direct kinematics. So, first, before deriving direct and inverse kinematics, we will look what is exactly direct kinematics. So, as you can see, this is end effector and this is workspace. This complete table, this is workspace. Okay, so you can draw an axis system. This is x-axis and this is y-axis. So every point in this workspace can be marked as p, x and y. Okay, so every point is in this workspace can be marked as a point p consisting coordinate points x and y. So if anyhow we can relate this point xy with angle theta 1 and theta 2, so that is inverse kinematics in the sense for given point p, if we can find out joint angle theta 1 and theta 2, direct inverse kinematics. And for given theta 1, for given theta 1 and theta 2, let me first introduce. So this is clear that this is point, and so angle made from x-axis, this is theta 1, and let me extend the length, this line, and from this line, this is theta 2. Okay, and for given theta 1 and theta 2, what will be the point x y, that is direct kinematics. So first we will derive relation for direct kinematics. As you can see, this is length L1. So projection of this L1 over this x-axis will be from this location to this location, and this will be L1 cos theta 1. Likewise, perpendicular this point, if I consider point A, so J to A will be L1 sine theta 1. Okay. So likewise, just draw a parallel line. So this will be theta 1 because this is parallel to x-axis. Okay. And this extended line is parallel to this L1. So that's why this will be theta 1. Okay. So complete angle will be theta 1 plus theta 2. Okay. So this, if this is into factor, and so projected length of L2 over the x-axis will be L2 cos. Now angle is theta 1 plus theta 2. So theta 1 plus theta 2. So likewise, this perpendicular distance, this will be L2 sine theta 1 plus theta 2. Okay. So now complete length. So complete length, because we are considering this point of end effector. So let's consider XE and YE. So this is XEYE. So XE will be, as you can see, this is this complete length from J1 to B. This complete length. So this will be L1 cos theta 1 plus L2 cos theta 1 plus theta 1. Let's say equation number 1. Again, YE will be this distance plus this location to this location. So this will be sine theta 1 sine theta 1 plus theta 2. This is equation number 2. So as you can see, for given theta 1 and theta 2, we can find out XE, YE, in the sense point corresponding to end effector. Okay. So this can be find out. So this is direct kinematics, and this is very simple in compared to inverse kinematics. Now let's find out relation for inverse kinematics. Okay. So as I already told you, that what is inverse kinematics? Inverse kinematics in the sense, for given XE and YE, what should be the angle theta 1 and theta 2? Then you can track, suppose that you are planning to track this trajectory. Okay. Let's say you are planning to track this trajectory. So this trajectory is combination of many infinite points. Okay. So corresponding to these points, anyhow, if you can find out theta 1 and theta 2, then you can move these stepper motors, and you can track automatically, this robot end effector will track automatically this trajectory. So that is inverse kinematics. So let's start finding. So just square both side of equation 1 and equation 2 and sum. So this will be x square plus y square, okay, equal to L1 square, as you can see, cos square theta 1, because I am squaring complete right side, okay. So like this. So a plus b square kind of thing. So L1 square plus L2 cos square theta 1 plus theta 2, okay, plus 2. So plus 2 L1 L2 cos theta 1 a to ab, so 2 L1 L2 cos theta 1 into cos theta 1 plus theta 2, plus now square of this, so L1 square sin square theta 1 plus this is L2 square, okay. So L2 square sin square theta 1 plus theta 2 plus 2 L1 L2 sin theta 1 into sin theta 1 plus theta 2. So now just by summing this complete right hand expression, you will find out L1 square plus L2 square plus 2 L1 L2, and here you can see why did this disappear, because L1 square take it common. So L1 square cos square theta 1 plus sin square theta 1. This is kind of sin square theta plus cos square theta. So this will be 1. Likewise, just by taking it out L2 square common, so it will be also, this will also 1. So L2 square plus 2 L1 L2, this is common in both. So 2 L1 L2, and now this will be cos C cos D plus sin C sin D kind of expression. So you can write cos, this will be cos C minus D, okay. So in the sense cos C minus D, in the sense you can write theta 1 minus theta 1 minus theta 2, or theta 1 plus theta 2 minus theta 2, both are correct. So actually this will be plus minus, okay, both are correct. So equal to so you can see this will cancel out, so theta 2. Now you can easily find out that cos theta 2 will be x square plus y square minus L1 square plus L2 square, this complete. So this complete expression can be written as divide by 2 L1 L2, okay. So this is complete expression for theta 2. So you can find very easily theta 2 is equal to cos inverse this complete expression. So for given xe and ye, you can find theta 2, but still we have to find theta 1. In this expression, everything is constant except this xe and ye, because this is L1 and L2 is constant. This is link length L1. This will depend on the robot link length. Okay. So let's consider theta 1. Now, how you can calculate theta 1? That is little tricky. So I will redraw this complete picture. Okay. So let me redraw first. That will help you a lot. So wait a second. So if this is x-axis and this is y-axis and this is L1, link 1, joint 1, joint 2, and this is extended length. Okay, theta 2 and theta 1. This is L2. Okay, now the coordinates of this end effector is xe and ye. We are planning to find out theta 1 for given xe and ye. Okay, let's draw a line from joint 1 to end effector. Okay, this is joint 1, joint 2, and this is e. Okay, now as we can see, let's draw a perpendicular line over the x-axis. Okay, so let's consider this is point C. Okay, now this angle alpha, let's assume this angle is alpha. Later I will find out value of alpha, but let's assume this angle is alpha. So this is, now this is complete right angle triangle J1 E and C. This is complete right angle triangle. So you can use trigonometric relations to find out relation between this perpendicular and base. So perpendicular upon base can be written as tan this complete angle, because we are considering this right angle triangle. So this complete angle will be alpha plus theta 1 equal to this perpendicular will be ye. Okay, so the coordinate of this point E is xe and ye, so this complete length will be ye. So perpendicular upon ye divide by base in the sense xe. So it can be written as theta 1 is equal to tan inverse ye upon xc minus alpha. Now still alpha, we haven't expressions for alpha, so we assumed alpha. Now the next aim is to find expression for this alpha. How we can find? So let's draw a perpendicular line over this extended line. Okay, now in this one is right angle, let's say this is D. So now this J1 ED make a right angle triangle, and this is alpha, this is perpendicular, and this complete length is base. So we know from J1 to J2 length is L1. So anyhow if we can find this length, so we can measure complete length J1 to D. So this will be, so as this is L2, link length is L2 and this is theta 2. So from this location to this location, this will be actually, yes, L2 cos theta 2. See, this is theta 2 in this triangle, okay. So this is base and this is perpendicular, and this will be L2 sine theta 2. So now this alpha can be written as, where tan alpha is equal to perpendicular in this complete right angle triangle J1 ED. This will be perpendicular in the sense L2 sine theta 2, L2 sine theta 2 divided by this complete base. So this will be L1 plus L2 cos theta 2. Okay. So alpha can be find out as alpha is equal to tan inverse L2 sin theta 2 divided by L1 plus L2 cos theta 2. Now everything is in this expression. See, YE, XE is for given, we are planning to find out value of theta 1 for given YE and XE. So this is variable YE and XE. L2 is constant. We have already derived expression for theta 2, so it can be calculated. So L1 plus L2, L1 and L2 is constant. Cos theta 2, we have relation for theta 2. So now we can easily derive this. We can find out value of theta 2 for given coordinates xe, ye of this end effector. So this is complete inverse kinematics relations for T2 link manipulator. So later we can use these relations to program two-link manipulator for drawing particular curves in two-dimensional space. So I will use Arduino IDE, but before that, before programming in Arduino IDE, I will simulate this two-link manipulator in MATLAB environment and in next section. So please try to derive these relations, because I will use as it is these relations in MATLAB environment to simulate this two-link manipulator. Also, later in later classes, I will use same relations to code this inverse kinematics in Arduino IDE. Thank you for attending this class. We will meet in next class, and that will be, I think, related to simulation, this inverse kinematic simulation in MATLAB environment. Thank you. Thank you very much.